there in Chicago, and I actually had a group of students, and it was a very relaxed environment, even though, people almost competing against the computer rather than competing against other teams. So it was very collegial and very, but it's a good experience. So I'm not quite sure if they changed anything on the format, but it was definitely fun. So what I wanted to show you today, and hopefully it'll somewhat helpful. I don't have a lot of slides, as you might see it, and I posted everything, the files on the URL that you see down there. This also includes the PDF of this presentation, and I hope that I just give you an idea, and basically what I want to do is walk you through the one of the problems, and how I approached it in the last couple of days. I spent a couple of hours trying to solve it, and maybe hopefully something rubs off and is interesting for you, and then you can hopefully have some questions, and I can help you maybe getting some pointers done. So now I need to find out how to go here. So quick outline. So basically, I looked at the last week's challenge, was the Drunken dude, and let's just get in here. There's a lot of wordy. Quick question, feedback maybe. Did anybody try to look at these challenges at the HPC University website? No? Yes. Okay. Oh, okay. Very. So, okay. What's that? It's actually helpful because I can't see the chat right now. That window, so I can't see the chat. I just see like a little screen popping up for a second. So let's just. But that's good enough. So thank you. So I just wanted, it's so hard to get if I'm not used to doing a one-way. Usually I'm standing in the classroom and can look people right straight in the eye. So this challenge, I hope, excuse me, was actually kind of fun, and you see from the wording. So if you had a chance to read the whole thing, so it basically is it goes, it's the Greek mythology. Sisyphus, the guy who had to roll up rocks up the hill every day, and then he had to do this for, I guess, his entire life, or for the entirety, whatever. So this is a simulation that is, or the problem is to simulate that in a 3x3 grid, where we have a drunken dude who has to carry rocks from one end up, or like from one side of the grid to the other side, and the dude does not remember where to go, so it's basically a completely random process. And that's kind of like, I don't know if you heard about the Brownian motion, or like, a random Walker process. So at any time moving one step direction, so basically the chances to go from one in any directions are equal. And so we kind of just simulate that. And the question is here to find out how long would it take to complete the task. And so, of course, the rules are kind of fuzzy. There are a few things in there. But let's say we have these rules. They are given. Fortunately, if you're at the competition, you will be able, if there's something unclear, to ask people around it. I sent an email, but I hadn't gotten any feedback with some of my questions. So roughly, to try to understand the problem. So the dude moves on the grid. The problem, basic statement was like a 3x3, but then of course in the back of my mind I would like, okay, how would it be on a 5x5 or 7x7? It was talking about the pedestals that are on one side of the grid, and basically once a rock is moved there, then it won't be, it sticks, and it won't be, it would be removed. So of course we need to have a final end of that. Um, the way I understood it, because it's quite possible that the Sisyphus could move a rock, carry a rock into another grid cell that already has a rock in there. Since there are no distinctions between the rocks, I just basically assumed that it would just take one. If he leaves the cell, he would just take one with it. And one of the things that was not expressed, but I assume it was that they're actually boundaries. So a lot of times, this is actually often you might have seen problems like that on a grid, for example, and often we use periodic boundary conditions so that we fold the edges. So what happens when you come to the left side? You basically appear automatically on the right side. If you fold these together, you get a tube, and if you then fold the top and the bottom edge together, then you would you create this kind of torus that you see on the left, and that would would simplify life a lot in simulations, because we wouldn't have to worry about getting on the edges or getting on the corners. Why is this important? Because the degree of freedom is different in these different cells. So that makes the code that I show you a little bit later a little bit more cumbersome, because if I'm on the top edge, on the top row, I can only go left, right, or down. So you see there, like the numbers indicate how many directions I can go. And the corners, of course, there are only 2 directions. On the edges, you had 3, and then anywhere else in the middle, you would have 4 directions to go. So these are kind of things I was considering about how to kind of create that. So my goal is, I want to create a simulation that simulates how this dude moves on the grid, and I need to make sure that I have a really proper random process running so that I can trust my simulation results. And then of course the logic that carrying the stones and everything has to be correct. So being faced with a problem like this, couple of design decisions. One of the things, okay, I need to use my computer, I need to program it. If you looked at some of the other problems, some of them have, one of the things that comes to mind is like, okay, what is my internal data representation? How do what is my data structure? What kind of variables do I need to, or values do I need to represent in which format? In this case, I think it's fairly straightforward. I need to have the position of the dude, of course, at any time, and I have to have the position of the rocks. That defines my environment. I decided to use a map, basically create a map and store the number of rocks per cell, rather than having the individual rocks and keeping their positions. And there was just a decision I made. There are often many ways to do it, so sometimes you might try to do one thing, and then of course it might not work out as well, might get too complicated, and then there's nothing wrong with backtracking and trying something else early on. So another decision, of course, is do I have any input data? For this particular problem, there are not really any input data, so that have to be processed. So I have some parameters that I want to modify, like for example the grid size, because even though the problem says this is for the grid of 3, but it would also be interesting to run it for larger grids and see what happens. And technically, of course, it should work the same way. And then probably because this is a typical problem where we have multiple simulation runs, so might have something in there like the number of simulation runs or other types of parameters.
Yeah, I'm going to stop for a second.
Mm-hmm.
If anybody has any questions at this point, we can do 1 or 2 questions and then go on. And what you want to do is type them, and if you type them, you actually are on the conference call as well, say that you're on the conference call and unmute now.
Okay, I saw the.
You see it?
Can you read it? I saw a question.
Well, the first question is from Pedro, and it says, "Is the initial position of the dude an input?"
In this case, it's absolutely. In this case, the problem says the dude starts in the center, but it's a good point. Yeah, I should put an input in there. If I have it as an input, then I could test if there's, for example, a difference if the dude starts in the corner versus the dude starts in the center. So, good point. So in this particular example, because the problem said the dude always starts in the center of the grid, I just left it at that. But, again, it's nice to play around with it, and even if you basically write a program to look at something, you might want to add something to it just because you get, other types of questions that come up.
Okay, and Pedro, of course, says a beautiful response, which is he didn't read that part.
That happens. Sometimes you spend a couple of hours trying to solve something and then realize it was already given to you because the instruction already said it. Happens to me all the time. So, okay. So the basically with this particular slide, all I wanted to is sort of bring up some points. I get asked a lot. About programming languages. So like, for example, with my students when we have projects, usually there are many ways to solve a problem in many different programming languages, and of course they all have their pros and cons. So some programming languages compile into faster code, some are more suitable for large software projects, some are not as fast, but they are easy to type. In particular, if it's a small, quick and dirty program that is just intended to answer a question. It's not a software that you want to use for other people to use, but it's really writing programs to solve your particular immediate problem. So there's a variety of programming languages, and I actually tried to not to be just to be limited to one. I try to keep current on a number of languages that I use, and often, rather than trying to put everything into one program, I actually might write different pieces of code in different languages and just tie them together so that the data, whatever one program produces, is then moved to the next program and it just processes. And sometimes that helps to get quick results, because certain things might be easier in one language than they are in another language. So and part of this, these kind of decisions are basically came in here. One of the things that is really critical for this particular simulation, for this particular problem, is that I can create a map or this grid where my dude runs and my rocks are stored. That's fairly static, so it doesn't change and I only need, for one run, I only need one representation of that. Other problems, like I looked at the problem that was the protein folding, we actually have to create, for the protein folding, you would have to create multiple alternatives, and that relates back to dynamic memory management. And dynamic memory management in C is possible, but it's a little bit of a headache. So other languages like Python or even Java, who do garbage collection and do something like this in sort of more built-in, interesting way, might be more suitable for that. In particular, scripting languages like Python, where you can create lists and you can add things at the end of the list without having overcomplicated container classes to use. So that would make that's also a factor that I would use to make a decision which programming language I use. So I wanted, for this particular program, I wanted to keep it very simple, and so this program is actually written in C, and it's plain C. Input, output are something I want to get rid of, I want to make really easy. Since I only have a handful of parameters that I sort of consider input, and I could actually add the starting position, I decided to not even put them in my program as like reading in these values, but rather define macros in C and then set these at compile time. So every time I run a simulation, I actually compile the program first. Since the program is just very short, it just takes a second. So I basically put it in my, I compile the program with the parameters I want, and then run the program. And my output is also, it doesn't have any text, it's just numbers. And of course, that only works personally for me because, I mean, because there's no explanation what these numbers are. But if you're writing a program and the program is just to solve your problem, then you basically know what you're doing. This is not for everybody else, so you don't have to spend a lot of time explaining or having some type of user interaction in there. I did a little bit though, because one of the things is, of course, within a few hours, I will forget what I actually did. So if I finished this yesterday and I want to come back today, I need to know kind of something to remind me what I did. So here are some tools that so basically this is going to be is completely written in C. So I'm going to show you the program in a while and then go through some steps. Again, keep everything very simple. Sometimes also what helps is, and a lot of people might not be too familiar with that, but it's definitely worth it, to look at Unix and look at a Unix command. So you see here so let's say, for example, I write a program sim that produces these numbers. So let's say my simulation program runs a simulation, and the output is really the number of days it took the dude to basically finish the task. And given this is random, we expect there is of course, every time I run it, I might get a different number. So if I run it 1,000,000 times, I would get 1,000,000 different days, and then what I might be interested in is a distribution. How many times out of these millions did it take 58 days? So let's say my simulation program actually runs the simulation and just prints out the iteration number and the value. I did that in the printf. If you're somewhat familiar with C, so I would print out, let's say, the number of iteration, the iteration run, and the number of days. That would be my value in 2 columns. The little program cut in on Unix and Linux, I can actually take a file that's basically it's rows of numbers and say I just want to have the second column, or I want to have just the third and the fifth. So this cut allows me to cut out certain columns. Then my output now basically would produce just 1 column. Then I can sort it. The unique command actually takes duplicate out, or unique with the option -C can also basically produces a number. How often did this value actually appear? Then the org command is actually not really necessary here. I just use that to actually switch my columns around, and then I direct everything into a data file. So what I actually created here is this line of Unix commands, and you see the vertical part is the pipe. So I start out simulation program, run through all these programs that already exist, and at the end what I have is actually a file that has a histogram. It has the values, the number of days, and how often these days appeared in my 1,000,000 or whatever simulation runs. That's a lot. And I saw, is there a question? Or just a gasp? What is that? So I see, got it. Okay, so I brought this out here just to say refresh your Unix commands. These tools can be very helpful and allows you, once you get from, they're kind of cumbersome because all of them have different options and stuff. But when you get a little bit comfortable, when you get comfortable with them, you can accomplish a lot of things very quickly. The other thing that of course, one of my favorites is GNU-plot. If you haven't looked at GNU-plot, it's usually, because it's fairly lightweight, it's usually available on every Linux system. But of course, you can also install it on your Mac, and I believe there's a Windows version. A quick program that can create fairly sophisticated plots, but it's also you can very quickly produce a plot, and it's fairly lightweight. So the command here, plot, actually to see this. Of course, what you see here, this picture is not what that is. I just took a random picture. But let's say I would produce that histogram, then all I would have to say in GNU-plot would basically plot hist dot, just the file. The rest is actually not necessary, but you can change options in there. Okay, so these are these are basically just some thoughts to say, okay, how do I go about it? How do I write my program? Now, when it comes to implementation, of course, the first thing I need to consider is the movement of the drunken dude. Then I need to make sure that I understand the programming logic so that the rocks are moved in a proper way. I need to implement that, and also, of course, test for the terminal condition. And then I need to be considering my input and my output. I already mentioned that, and I think it becomes clear if you're not familiar with C when I show you the program, to basically create the how I just basically set macros and then define at compile time what these values are. And then also for the simulation to results, I actually just used standard output. So I just use printf, it comes on the screen, but then I can redirect it on the Unix. I make use of that to redirect it into a file, or even if I want to process something else. So that way I don't have to do any file management, I don't have to open files, and basically every time my program just produces a sequence of numbers. And that's about it. It sometimes might not be possible to do it just as slim, because you might have different results. But then again, there are also ways to put everything in one file and then use commands like grep to just extract the information that you want for a particular way, rather than trying to create a more complicated way in terms of opening files and writing files. The reason why opening a file is even though it's fairly it's very simple, but imagine you run your program. So let's say you run a program and I just call it output.dat, and it produces a file, output.dat. But now let's say I want to run multiple instances of my program in the same directory, and they all call them output.dat, then I get a conflict. So if I need to make sure that my programs might run, let's say, for example, I might run multiple processes on different nodes, but they share the file system, then I would have to make sure that each of them has a unique file name, and it just adds another complexity to it. So sometimes it's easier to avoid that. Yes. Okay. I appreciate it, sorry. Okay, so let me pull out my program, and actually, and these files are on that website, and we can bring that up again. Let me actually see first how, if I find my proper...
And you're setting it as full screen for people.
Yeah, where,
In the big rectangular box towards the top right, there's a button that says full screen.
full screen. I think it is full screen. Now this shows my, so can you see, so you saw the slides, right? Can you see the terminal now? Let me make this really big.
You do not have a screen there. That's better, I think.
So, can you see a text terminal?
Yes.
Okay. So this is actually, here's my files. Okay. So my program, actually let me run it first. And what I did is, and I show that in a minute also, I created a shell script. This is really the power of the command line. I probably don't have to preach to you, but it's so in my blood because I feel like every time I need to talk to explain people how powerful command lines interfaces are and how powerful it is to script and being able to script and all these hidden gems that a Unix system has to offer. So I created the script that actually calls my simulation program. It's called Drunken, and the first thing is, here I actually use some input because it's easy and I sometimes forget. So I basically, if I say Drunken, it reminds me these are different ways I can simulate my Drunken. And so if I say Drunken anim, it produces a simulation of this here. I hope you can see that. We see the you see the grid, should see the grid, and you see the numbers. The numbers indicate the rocks, and then the D stands for the dude, how it moves on the grid. So it's helpful to have something because you might just dive in and just produce the numbers, but there's so many times you can make errors, and it could be a very simple error, but if you just get a number at the end, you know, it could be wrong. You could be wrong. So it's good, you know, diving in. And of course, I don't want to spend a lot of time to create some fancy animation, so I just did basically this simple thing on a terminal screen, and it pretty much works on every system. It just basically uses printf, and then I use clear screen, the clear command to just clear the screen. But running this, it looks like it's doing what it's supposed to do. I can watch it. I don't know if you noticed it. There was one time when on the pedestal up there were two rocks, and then the dude moved to the other side, to the right, and it took one rock with it. So I think my programming logic is correct.
So does anyone have any questions at this moment? Might be a typer. So you have here, Peter, are grad students and undergrads ranging from freshmen through getting their PhD.
Mm-hmm.
About to become faculty, and there are some people who just started their journey. He wrote, can he run the program again, please? And Latifa said, no, I don't have any questions yet.
Okay. So now I'm actually, yeah. So I'm actually now running it as with a 5 by 5 grid, but and of course it, you know, can take time, a lot of time. Let's run it again just with the 3 by 3. You see how the dude just picked up one and it was moving to the other one, so it's just moving one rock, even though there might be another rock in the cell, then the other rock stays. And one of the things is very hard is to really observe if this is random. And sometimes it looks like kind of odd. Is that really random? And so one of the biggest questions is, or one of the concerns is that we always have, particularly when we do computer simulations, that we have a good random number generator. And the standard C function used to be poorly implemented, and there were a couple of things you shouldn't do, but it got much better. And even though there are better random number algorithms out there, and or generator algorithms and libraries that have that, we're probably good here, but I also implemented something to check if it's really correct. And so what I did is I have one version basically that of my program that lets the dude run just randomly without any rocks or anything, just for a long time. And I wanted to see what is that the cells are visited equally often. So that would give me an indication that my random number generator is not biased, and I actually really get into every cell with equal probability. The solution on the website that is posted now has something in there that I'm not quite sure. I haven't tested that part, but there might be. I think they have a flaw in there, but I haven't tested it. So, so I can run my random number generator, and I think it does by default only. Oops. So what it runs my program and it produces a plot here. As basically I run, so as you can see, my program here, that's the Drunken dude, is actually a shell script. It runs the simulation, and then it takes the data file and produces a GNU plot file right from it. So this is actually my 3x3 grid, and it plots from
1 second, the dinosaur computer that I was using just
okay, let's see.
turn on the, I'm going to turn off the volume.
Brought the slides back up. This is the URL where you can actually, if you're on a computer, you can download the files from there, if you as well as the slides. So what I wanted to do is, of course, kind of give you some idea about how I processed it, and so basically I ended up writing 2 programs. But more importantly is I think it's to share my thoughts and how I went about it. So the simulation seemed to run. I did I did something which is basically is GNU plot, to just have a test run where the Drunken dude runs on the grid, and I just count, basically use the grid just to count how often the dude was in the on that grid point. So if I do only a 1,000, so on a 3x3 grid, we get something like this here. That's basically, now of course we only have one cell that represents the center, and then we have the edges and the corners. If we increase that, I mean basically just to test how well our random number generator goes, we would get something, I use a larger grid, and then I get the edges here, and they're less frequently visited, the corners are even less, and then the middle field is fairly evenly visited. But it also, of course, it depends on the number of iterations. So if I only run this on 10,000, I still get quite some differences in here. But the numbers go down. And so if I have more iterations, so this one here has 10 million, that's it. So I assume that my random number stuff works okay. Let's actually run simulations and find out how long it takes. And so let's go straight to the result. And the odd thing is, and I haven't had enough time, so let me just run it. And I can, I think by default, I can set it up to run for 1,000 times. So let me do 10,000. It might take a little bit. Nope.
Let me remind people that you have to mute your phone.
So so the simulation program runs, and I actually set it up. It produces a an output, and my output files have the two input parameters that I have: the size of the grid and the number of iterations in there. And so if I run it 10,000 iterations, then this is basically what it looks like. It gets me the iteration number. What does it get me here? It actually gives me the histogram. It gives me the days and the number of times. So I already basically produced it to create that histogram, so that it actually here, like 30 days, 54 times it has been 30 days. So what I get is the first column is the number of days, and then the second column is the frequency, and then the third column is just the divided by the total number of iterations. So I do that. So I get 3 columns here that I can then plot, and this is actually done again using GNU plot, and produce a plot, and this is how it looks like. So oddly enough, it looks like and that's really interesting, and maybe, worth to explore. Maybe, I get a really odd result here. I actually get sort of two Poisson distributions, and they're fairly good. If I increase the number of iterations, they get smoother and smoother. So we definitely have a good distribution with a peak, but what's interesting is that this almost looks like one distribution that goes with the odd days, which I think is the higher one, and then one with the even days. So it's like it is sort of two separate types of outputs. If you take all the results from odd days and all the results from even days, you would actually get two very smooth distributions. And the peak is about the same. So I found this interesting, and the question now, of course, is like, if this would be a scientific result, is that something to publish, or do I have an artifact here that is part of my programming error? And so it looks really cool. I think I did everything right, but I don't know if anybody has explored that, but it seems to be an unexpected result. So as a scientist, if I have an unexpected result, of course I'm excited and I hope I can write a paper about it. But then as a computational scientist, there's always this daunting thing in the back of my head, like, well, where's the programming error? One little error could have been just producing these artificial results, which have nothing to do with reality. And so I just encourage you, I don't know if you, how much it makes sense to go through it. This is the Drunken dude is a shell script. What I do is, like, the different parts. You see, for example, if I do an animation, you see the line that says GCC, and it basically, what you see there with the -D, those are my macros that I define. And I just define those values in my shell script rather than in the C program. The shell script makes it easier to have input, and then I can use the same variables to produce. For example, here, if you scroll down, I use that to also define the output name, and then also feed it right into GNU plot. So my script also produces a plot right away. My program is the Sisyphus here. I have roughly to go through that. I create a lot of global variables because I'm lazy. This is really bad programming style, but again, I need to write a program that gives me an answer quickly, and after that I discard it. I mean, I keep it because, for the results, but it's not a software project. So I try to keep things simple, which for once, global variables. And one of the things in C is that global variables have to be, in C it's very static, so all array allocations have to be static. So n is actually a constant parameter, it's not a variable, and that's why I define it as a macro. So if n is not defined outside my program with the compiler, it will be defined by 3. But this is what the preprocessor says. So I did a lot of stuff basically taking care of at the compile time. I have a couple of functions that put the output together, which ended up later. I created a function random choice, and that is basically to see where my new position is. So I broke it up. I don't know if it's the most elegant way to do it, but I broke it up that depending where my, if for example, if the dude is in a corner, there are only 2 choices where it can go, and if it's at the edges and so I have all these different cases in here. There was a lot of cut and paste, and I have to make sure that I don't make a mistake in there. That's why it's important to to simulate that. Other than that, is probably the most complicated part of that is the just to define like what is the proper movement, and I made that this function produces like a basically a delta x delta t and a delta y delta x, and then I just change the position from that. Then like basically I have these different parts, like for example running creating that random walk, or to run the simulation. I just again use conditional compilation. That way I can keep everything in one program, even if my program does different things, but then it allows me to keep those things together. If you're somewhat familiar with C, you should be able to read that, and hopefully it's not too complex. So that was kind of fun. What I didn't do, answer the question, because it asked for the mean day, and I haven't put that or the average day, I guess, and that would come out of 1,000 simulations. But I give you instead a distribution, which I thought was much be more interesting. CISCAUEDU/XSEDE. So this is the URL where you audit the 2 programs, and there I tried to run it. It runs on Linux as well, without any changes. So that it run Mac OS if you have, and if you don't have GNU-plot installed on Mac OS, then you need to comment that part out. But most Linux systems have GNU-plot, or you can easily install it. And of course, if you actually find that code somewhat interesting and have some questions how I did certain things, I'm of course more than happy to answer questions. So the question about the correct about the decimal places, I think I wasn't quite sure what they meant with that. But then when I looked at, if you go to the HPC University's website, there's another example program, and let me pull that up. This is actually what they had suggested. What I did is also basically have a simulation and then just average. So you run many simulations and then you average over it. That's basically what they that was apparently the answer, but I wasn't quite clear about it either. I sent them an email, but I never got a response back. So fortunately in a competition, or hopefully in a competition, people can clarify that, because it's, yeah, all you could expect is like a and then I guess they just want to see, well, I guess you should get there should be a correct answer, but the precision would depend on how long you run it. If you run it for 1,000,000 times or 1,000,000,000 times, which then during the competition might be interesting to see who can run it the longest to get the most accurate result.
So,
There's one question about parallel I can answer real quick. This is a nice problem because it's trivial. All you need is each simulation run is independent from the other one. So yes, you can, if you basically just want to produce as many simulation runs as possible, you can just populate it on all the processors, run it as long as you want to, and then collect all the outputs and then do the aggregation on that. So this is a nice example of a, what they call it, a trivial parallelism. So like on a little fee, I wouldn't even modify the code. I would just run it on different processors. Okay. Will we have access to?
Not certain what Shannady's question is, so Shanady, why don't you unmute yourself and state your question? You say, will we have access to the ability to signal discussions that are coding for the next challenge? My answer would be we have 5 more weeks in each. Give me your question, and why don't you state your question? Okay. So for our group, we have 5 members, and we were trying to meet on Skype to discuss the solutions we were coming up with for each of the challenges together. So my question is, if we're going to discuss like our intermediate coding strategies for our next coding challenge, should we do this on a regular basis so that we can share like the solutions or the way we're coding our coding techniques? Well, I'm going to answer that with a yes. And if you need the Adobe Connect platform to do it, I can give you the access information if you email me. Okay. Yeah, because I wanted to do it through Skype, but if the platform is available, it might be easier to use it so we can share our data and get to know each other a little better for our next before. Yeah, and if you don't have a 10-year-old computer that just crashed and another computer that had a dead audio card, I bet it would actually work well for you. Yeah. Okay. Well, I'll go back to the view chat one second. Nara has a question. Oh, it's been answered already.
There's one about how to parallelize it in C. Again, if you have a multi-core system, you might just use OpenMP with a simple parallel region or a parallel array. Just make sure that you basically have each of these data structures are independent, because at the end you want to run a lot of these. It's kind of like what we see a lot of times, like how to compute pi or simulate the Monte Carlo simulation of or computing pi. So each run is completely independent. Yeah, I wouldn't mess with MPI. That's always not for this problem. I would rather send jobs to each processor individually and let them run it 10 million times and then collect the data afterwards.
Okay, it's 1:07. Peter, do you have any parting words?
I hope you got something out of it and appreciate your patience, and it was fun for me, so hope it helped a little bit, and I see you at XSEDE in July.